going to look really familiar because it's almost exactly the same as MOSFET amplifiers, except stuff has different names and there are more models. Other than that, it's almost exactly the same. We have 3 types of BJT amplifiers. Remember, we had 3 types of MOSFET amplifiers. We had common source, common drain, common, whatever that last one is, common gate. So we have the exact same configurations with BJTs. We have common emitter, in which the emitter is common to both. So we have VBE in and VCE out. So the emitter is common to both the input and the output. It also happens to be grounded, and they frequently are, but it doesn't have to be a common emitter. As you have seen, when you have an emitter bypass resistor, you can actually not be grounded. Common base is the other one, or the next one, where the base is grounded, and so the base actually appears at the bottom. VN is VEB, and V out is VCB, so the base is common to input and output. And the last one is the common collector, which is analogous to the common gate. No, it's not. It's analogous to the common drain. I am really tired because I was up here at 7, so I've been here forever. I left home before 6. Anyway, in this case, the collector is grounded, so it also kind of appears at the bottom and is common to both the input and the output. You have BC going in and EC coming out, so that is sort of the very basic ways of classifying the 3 types of amplifiers. We're going to look at each kind, and then the last thing we're going to do is look at discrete amplifiers for a minute, which are basically the whole circuit, kind of like the homework problem, like the second to last homework problem you have. So the common emitter amplifier is the most common type. It is similar to the common source in MOSFETs. And we need to know amplifier gain. Remember, AVO is the gain of just the amplifier. AV is the gain of the amplifier, usually with the load. And then we have input resistance, output resistance, and overall gain. So exactly the same stuff that we wanted to know for the common source or any other type of amplifier we have. So the first thing we're going to do, last time we talked about the different models that we have. We have a transconductance-based model, but we also have models that are based on alpha or beta, depending on how we use them. And for the common emitter, we're going to use the transconductance-based one, and you'll see that the answers that you get are almost exactly like MOSFET. With the others, we're going to use a bit of a different way of looking at them, just because this is kind of how the circuits end up working out more simply. So if we replace the BJT with the pi model, and we don't have an RO, so we just leave that out, this is basically what the circuit looks like. AVO is defined to be V out over V in. V in is VBE, and V out is minus GM VBE RC, since GM VBE is the current, and it's going in the opposite direction, so that's where the negative sign comes from, and it's going through RC. So that just uses Ohm's law, and then we can cancel VBE, and we get minus GM RC, which is pretty much just like MOSFETs. MOSFETs was minus GM RD. So it's not different. It's really, once you get to the point where the amplifier, it's pretty much the same process, at least for this. If we add a load resistor, which we can do, we're going to, we get R in and R out. R in is R pi, which is, remember, beta plus 1 times little re, and R out is RC. If we add the load, we'll get just RC in parallel with RL for the gain, just like the MOSFET amp. And then the overall gain is different, because remember, with MOSFET amps, the gain of the amplifier, including the load resistor, was the same as the overall gain, because the input was always infinity when you had the input at the gate. And with a BJT, that's not the case, because the input resistance is not infinity. it's actually in this configuration R pi. So that means there's a voltage divider between our in and our signal. So you end up with actually a different equation for the overall gain. So this is one way that the BJT amps differ from MOSFET amps, in that you have a voltage division at the input, as well as technically you have a voltage divider at the output. We just don't portray it that way, but you would get the same thing if you had RC times RL over RC plus RL, or RC in parallel with RL. You get the same thing. So we don't usually put that voltage divider in at the end. So slight differences, but not major ones. Characteristics of common emitter amps: the input resistance is moderately high, but it's not as high as a MOSFET-based amp like this, so it's not quite as high. The output resistance is moderately high, which is not necessarily a good thing, because that's going to be whatever RC is. The voltage gain is actually much higher than with a MOSFET. The actual overall voltage gain always ends up being significantly more, depending on the circuit. The input resistance is inversely proportional to the collector current, but gain is proportional to the collector current. So there's actually a trade-off here, where you could make the input resistance bigger, but then that's going to make the gain, it's going to change the gain somewhat. So that's one of the kind of trade-offs with this type of amp. And then if you lower RC to make the output resistance lower, then you also lower the gain. So there's a little bit of, interaction. It's similar to the interactions we had with MOSFETs. So what was the second amp we did with MOSFETs? We did the common source, and then the next one we did was the common source with a resistor, a source resistor. Remember that? We have the same thing with common emitters. We can put an emitter resistor there. We call this an emitter degeneration resistor because it makes the overall gain go down. That's why they call it that. The T model works better than the pi model in this case because of that resistor, because the emitter is not grounded. So we're actually going to use the T model to analyze this. And when we do that, remember, and this is the same as with the MOSFET amp, Vn and VBE are not the same, because now Vn goes from the base to ground, and the emitter is not connected to ground. So Vn is actually VBE plus IERE. And then Rn is not R pi, it's something different, because there's another resistor in series with little re. Remember, R pi is just equal to beta plus 1 times little re. And in this case, we have little re plus big re. That's the only way I can tell them apart. If I talk about re, there's two. One of them is a resistor, and one of them is a resistance. But we have to combine large RE with little RE and take that into account as far as the input resistance goes. The output resistance is the same as a regular common emitter amp, so that is not going to change. It's still RC. So when we take that and we look at the circuit, Rn is defined to be Vn over In. Vn is IE, the AC version, times RE, little re plus big re, and that gives us that value there. And then on the bottom, In is just equal to IB, the base current. So the base current is equal to beta plus 1, or IE is equal to beta plus 1 times IB. So that's how we end up canceling out IB, and we just end up with that beta plus 1 there. So whereas before we had R pi, which was beta plus 1 little re, now the input resistance is just beta plus 1 little re plus big re. That's the only difference, is the input resistance ends up being larger. For the gain equation, remember AVO is defined to be V out over Vn. V out is going to be minus GM VBE RC, and the in, that was V out, V in is going to be little VBE, then plus GM VBE RE. Okay, then we can cancel all the VBEs. We get minus GM RC over 1 plus GM RE. Again, that's pretty much exactly the same as the MOSFET amplifier was. The MOSFET was minus GM RD over 1 plus GM RS. So it's the same basic equation, it's just presented with different values. If we add a load resistor, it's in parallel with RC. So we put it in parallel with RC, not with RE. So it appears on the top, the numerator of the fraction. It does not appear on the bottom. So we actually take into account that way. And then again, the overall gain is not equal to AV because this is a BJT-based amplifier. So we have a voltage divider where we take Rn over Rn plus R signal times AV. Rn is going to be something different than it was with the previous amp, but it's the same general idea. Once we find Rn, we just take Rn over Rn plus R signal times whatever AV is. We can compare the two, the common emitter with the emitter resistor and the common emitter without. The input resistance is higher with the emitter resistor, which is a good thing. The output resistance doesn't change. The voltage gain goes down, which can actually be a good thing because sometimes the voltage gain of BJT amplifiers is way, way too big. So we want to reduce it down to some manageable level. So that's not necessarily a bad thing. It's just a thing, not really anything bad or good, just a comparison. The overall gain is less dependent on the transconductance, which could be good. And then the external resistor RE is what causes all of those effects. It has a feedback effect that actually produces all of those different effects, which makes sense. It's the only thing that is different between the two. So it would make sense that it's the thing that is responsible for all those. So those are the two most common. I'll tell you now that on the next test, I only usually put common emitter type amps, so write that down. The homework includes a common base and a common collector. Lab includes a common collector, so I don't tend to worry about that on tests. So don't worry about common base, which we're going to do next. Doesn't mean you can't listen. It just means, you can. I may ask a sort of a conceptually kind of question, but that would be so simple. It wouldn't be complicated. So common base is analogous to the common gate with MOSFETs. The input's at the emitter and the output is at the collector. And this amp has a few problems. We can replace this with the T model, and Vn is equal to negative VBE coming in. Rn is actually equal to little re. Does anyone remember on what order of magnitude little re ends up being? Yes, it's like tens of ohms. So that's not good. That's generally a not good characteristic of this type of amp because the input resistance is so small, you end up losing a lot of input voltage dropped across our signal, and it doesn't actually get into the amp. Our out is the same as the other amplifiers that have their output at the collector, so that's not a surprise. When we go through and find the actual unloaded gain, that's defined to be V out over V in, and V out is just going to be minus GM VBE RC. And I do have a different model sitting there where I don't have GMR VBE there. I actually have alpha IE, and there's a reason for that. So you could just as easily use the other part or the other model. But anyway, we can get the gain this way. It's the same which is why I sort of included it as a GM based output rather than a alpha or beta related one, but you can actually change this. The value of GM is approximately equal to 1 over little re. Little re is approximately equal to 1 over GM. They're not exactly equal to each other. So an alternate way of getting the gain with this would be RC over little re. That would be another way to do it. You would get pretty much the same answer. So sometimes the gain equation is presented that way, and sometimes it's presented as GM-RC, but you'll get the same value. And in fact, for a common emitter, you could do minus RC over little re, and you would, again, get the same answer. So if we take a load resistor and we also, I didn't draw it in, I don't think, with the load resistor, we also look at the voltage divider for the overall gain, we get the same kind of voltage division we got before, where we have Rn over R signal plus Rn times GM times RC in parallel with RL. But we're going to move this around and get a different equation out of this. You could use it this way, and that would be fine. That's exactly the same as the common gate format. But it is often, with BJT amps, more common to just use resistor values and little RE values. So we can actually change this a little bit. We know Rn is equal to little re, and we actually know that Re times Gm equals alpha. They're not exactly, so we can't take one and the inverse of the other and get 1, but we do take one and the inverse of the other and get alpha. And remember, alpha is really, really, really close to 1. That's why we can make this as an approximation, because it's really, really close to 1. So we can actually take the Re in the numerator and substitute alpha, and we get this alternate equation to give you the gain. It's not, either one will work. The top one will work, the bottom one will work. Either one will give you, hopefully give you the exact same answer, we hope. But either one will work. You just often with BJT amps see the gain represented as just ratios of resistors rather than using transconductance. So, common base amplifier characteristics. Input resistance is really low. So, using a current source helps. Sometimes you don't have access to a current source, but it generally needs to be driven by a constant current rather than trying to divide voltage going in. Output resistance is moderately high, just like anything that has the output, the collector. The voltage gain is medium to high, but you lose a ton of signal with the low input resistance. So you'll notice that to get the gain of a common emitter amplifier and a common base amplifier, they're really the same equation. It's just the common emitter has a negative sign. So they should come out in the same order of magnitude, and they do, but it's that voltage divider at the beginning that changes their characteristics. So that's why a common base doesn't give you a higher overall gain, even though it has basically the same magnitude of gain as a common emitter. It does work really well at high frequencies. That's probably its saving grace and why it exists at all, because there is a type of interaction that happens with feedback capacitance with common emitters, which we don't cover in here because we don't cover frequency response, but there is feedback capacitance that occurs with common emitters that does not occur with the common base. So if you're using high frequencies, it actually works really well. So what is generally done is it's used in combination with something else. And there is a type, and I've talked about cascode amplifiers last time when I talked about common gates, but basically it's a common emitter connected directly to a common base. The common emitter is designed such that it actually has a gain of -1, and then it's connected to the common base, but the way it's matched up, because the collector of the common emitter is connected directly to the emitter of the common base, you don't have that loss of signal between the two. So basically the signal just goes right in, which makes it kind of like having a constant current source driving it. So then you get an overall gain that's almost exactly like a common emitter alone, but it works better at high frequencies. So
conceptual swing off this page?
Maybe. It's not even that common. I mean, it's not even that, I don't think they're even that complicated. I don't do complicated conceptual questions in here. I do really, really simple ones. But, that would be a good thing to know. That actually gives me some ideas.
A good performance at high frequencies.
Yeah, good performance at high frequencies is something you should know about common bass amps.
Exactly. That should be on the
It's-
test. Make sure we know.
Yeah. The common collector is, I think you build one of these in lab. If you've had lab already, then you already built one. If you haven't had lab yet, then you haven't built one. It's similar to the common drain. Remember, with the common drain, you had an overall gain of close to 1. So you would expect a common collector, which is also called an emitter follower for the reason that it is a good buffering kind of amp. We can take this and replace it with the T model. VN is similar to VN when we came in before with the common emitter with the emitter resistor. The only difference is with the common collector, we actually put RL in the position of the emitter resistor. So we actually kind of use that as our load. Not always, but frequently. Rn, again, is beta plus 1, little re plus RL, which is just in the emitter slot. So it's similar to the common collector with an emitter resistor. R out is, I did not go through and derive this for you, but basically R out is little re, but then since there is an interaction, this resistance is actually seen, but it looks beta plus 1 times smaller on the front side of the transistor. So if you had IB going through here, and then if you looked at it here, you would have IB times R signal, and here you would have IB times beta plus 1, which would give you RE times R signal. So when we reflect it to the other side, we kind of have to divide by it to get it to equal, if that makes sense. So we just take that resistance and divide by beta plus 1 to bring it to the other side, and that's what it looks like. The gain is similar to what we did before, V out over V in. V out is just IE times RL, and V in is IE little re plus IE big RL. So we can cancel out all the IEs and we just get RL over little re plus big re. And since, no, it's not RE, it's RL. Sorry, taught this for 20 years when we always used RE, and now we're using RL, so easy to confuse me. Anyway, if RL is much bigger than RE, which it frequently is, the gain is going to be approximately 1. It will never, ever, ever be bigger than 1, ever, because it can't be, because RL is in the numerator and the denominator. So the voltage gain, Rn over R signal plus Rn AV works. And actually, what ends up often happening is that we can take Rn, R signal, Rn, and AV and make it again into a big ratio of resistors. So Rn is beta plus 1, little re plus RL. R signal doesn't change. But then we again replace Rn with beta plus 1, little re plus RL, and then we replace AV with that resistor ratio. And what we hope is that we can cancel stuff. So I just put it up at the top here, and we can actually take RE plus RL, and we can put beta plus 1 under stuff. So I'm going to just move things a little bit. What I did was I divided everything by beta plus 1 to get rid of the beta plus 1. And now I've got RE plus RL on the numerator and RE plus RL in the denominator. So I can kind of cancel that. And we end up with RL over R signal over beta plus 1 plus little re plus RL, which is pretty much just a voltage divider. That's all it is. Because if you look at the signal comes in, it goes through R signal, then through RE, then through RL. And if we were to equate that and make it all have the same current, our signal would have to be divided by beta plus 1 to have the proper current in it. And so basically that's all it is. It's just like a big voltage divider, which means that if RL is bigger than the other two, you end up getting close to 1. Input resistance of these is high. That's great. Output resistance is low. Voltage gain is 1 or less. The bigger RL is, well, there you go. Thank you. The closer you are to 1. We use this oftentimes as a buffer between stages because it has a very high input resistance, very low output resistance, so sometimes it makes it easier to match up stages of amplification. And as I said, it's also called an emitter follower. So let's see what I have left. Yes. Okay. So I'm going to do a quick kind of example, and it's not complicated. We have a common emitter amplifier. We have BJT. We have the value of beta. We already have IC, so we don't need to do any DC analysis. And we have RC. Then we have a source with R signal equals 5K and a 5K load, and we want to find R in, R out, AVO, AV, and GV. Try saying that fast a bunch of times. GM is just IC over the thermal voltage, so we get 40 milliamps per volt. We can find R pi, because we're going to need that for R in. That's just beta over GM. That's one of the ways of finding it. There are other ways, but that's one way, and we have both those values. So we get 2.5K. R in is R pi, and R out is RC. So that part is done and simple. Most of this is just plugging in numbers and getting answers. AVO is just going to be minus GM RC, which I'll go to in just a second. I know it's all online anyway. So we can go through and calculate that, and we get negative 200. So that's a typical open amplifier type gain for a BJT. It's big. It's a lot bigger than MOSFET amps. The overall gain, if we put RL in parallel, we basically just cut it in half because 5K is the same. Or we can use a ratio of resistors times AVO, and we get the same thing. So basically, if we took an output voltage divider and multiplied by AVO, we would also get the same value. So there's, again, more than one way to do that. And then the overall gain, we just use a voltage divider at the beginning between R in and R signal, and we get minus 33.3 for the overall gain. If we were to actually put a signal in, we would probably, let's see, if we limited the peak input voltage to 5 millivolts at the base emitter junction, it might be more coming in, but it's going to get divided down until we get there. We want to have the peak signal voltage and the peak output voltage. So the peak signal voltage, basically we're just unvoltage dividing at the input. So we're taking that value of VBE and we're figuring out how much did it decrease from the signal to that point. So we're going to take Rn plus R signal over Rn. That's just the upside down voltage divider to get it further back. And we get 15 millivolts for the signal. And then the out, we just take that signal and multiply it by GV, which we just calculated. And we don't use the negative sign because we are doing peak. We're not caring about. So we end up with 500 millivolts. Yes?
Is the hat just to denote that there's a limitation on it?
The hat, it just means peak. That's like the standard peak value thing. So that's one example. The other one has to do with a common base. The common base amp is pretty much in exactly the same state as the common emitter. So it's going to have the same collector current, the same RC values, the same signal and load resistances, and we're just going to go through and find the values again. So GM is going to be the same because collector current's the same. Thermal voltage never changes unless you're in someplace really hot or cold. So that value is the same. RE is going to be 1 over GM. Again, that's approximately, but it's close enough to be reasonable. And that means Rn is 25 ohms instead of 2.5 kilo ohms like it was in the last problem. And Rout is the same. It's still 5 kilo ohms. So when we look at the gain, we're going to end up getting almost the same numbers to begin with. We take GM-RC, and we get an unloaded gain of 200. Last time we got negative 200 with the common emitter, we get 200 for the common base. So again, it's almost the same. When we add a load resistor, all we're doing is cutting the gain in half because it's equal to RC. So again, we have the situation where it's cut in half, but when we add the input resistance voltage divider between Rn and R signal, the gain goes way, 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 way down. Yes?
Sorry, I lost you at RN. Is that also
Little RE.
little RE?
Yes, yes. That's why these amps are so awful, because the gain went from 100 down to 0.5 because of the input resistance. Whereas with a common emitter, we had the exact same situation, but because the input resistance is bigger, we got like a gain of minus 33. So that's basically what happens if you just try to use this as an amplifier by itself. It ends up getting rid of the signal. Last thing, this is like literally, I think, the last topic. It is. I'm going to talk for a minute about discrete amplifiers. These are amplifiers that are built as basically out of components and include everything that you would have, because we really haven't talked about the bias circuit, looking at the bias circuit and looking at the amplifier, looking at it all together with all its different parts. The last problem in the homework is like this, so it should, no, not the last one, the second to the last one. I always say the last one, but the last one's simulating, so really it's the second to last. Anyway, a discrete amplifier circuit looks like this. There are coupling capacitors that basically isolate the AC and the DC circuit from them. So CC1, CC2, and CE all basically look like shorts for the AC circuit. They look like open for the DC circuit. The capacitor across the emitter resistor, it ends up allowing that emitter resistor to not appear in the gain equation. So when you're looking at the overall gain, the common emitter, or the CE, the capacitor there, basically shorts that point to ground, but only for AC. So as the DC circuit, it still has its bias information intact, but for the AC circuit, the emitter resistor is not there. So the middle part, the bias circuit that's inside the blue, that's the actual bias circuit. So if you're doing DC analysis, that's the part that you would do. And if we looked at the AC circuit, we would have 0 volts at VCC and 0 volts right at the emitter because of the either turning off DC for analysis purposes or shorting across the emitter resistor. Either one of those would work. So when we take this, we can put this into our model, and we can find Rn, Rout, AV, and GV. Now, Rn is now going to include all the bias circuit parts because it has to, because the bias circuit is part of the amplifier. So Rn is actually behind the two base resistors. So when we take our value of Rn, we have to take the two base resistors in parallel with R pi. That's why base resistors are usually large, because their value does appear as an input resistance when you're using a discrete amplifier circuit. R out, since RO is in the circuit, R out is going to be equal to RC in parallel with R out, and RL doesn't appear until we do the gain equation. The gain equation is just minus GM R out in parallel with RC in parallel with RL. And then the overall gain is really pretty much the same. The negative sign moved from in front of GM over to in front of Rn. It doesn't mean that that's a negative resistance. It just moved. I just moved it. So the format of figuring out the gain is the same. It's just Rn mostly includes those base resistors as part of the actual circuit. Another thing that can be done is that you could actually adjust the gain of one of these amplifiers by using two emitter resistors. You can use one that's unbypassed and one that is bypassed. So what ends up happening, RE1 appears as part of the DC circuit and part of the AC analysis, whereas RE2 disappears in the AC but is there in the DC. So there's a net RE for the DC circuit that's RE1 plus RE2, and then when you actually analyze the circuit, RE2 doesn't figure in, just RE1. So then when we take this and we use the T model for this because we have an emitter resistor, Rn is RB1 in parallel with RB2 in parallel with beta plus 1 Re plus Re1. So that follows the same pattern as the emitter resistor problem from before. And R out is still RC. Then the gain ends up being minus GM RC in parallel with RL over 1 plus GM RE1. So it follows the same pattern as a common emitter with an unbypassed resistor. And then the overall gain, you just have that same voltage divider. So hopefully you see a theme in how you get the gains of all these. They are actually pretty much the same. It's just that Rn may be really different depending on the circuit. Our signal is always going to be the same. Also, if you were to set RE1 to be an adjustable resistor like a potentiometer, you can build a circuit that has an adjustable gain. So you can actually just turn the potentiometer, change RE and that unbypassed part, and actually make the gain go up and down at will, depending on what your desires are.